Hello Dr. Dino, and good afternoon to everyone watching this video. My name is Fath Rahman Ahmed Mahjoub and my ID is 1095047. Today I will gonna present chapter 7 from page 14 until page 27. So in this part I will present diffusion and how diffusion works. I will explain the main ideas in this chapter. So first, diffusion is the movement of atoms from a region of high concentration to a region of low concentration. The process happens naturally in many engineering materials, specifically when the material is heated. So we started with Fick's first law of diffusion. This law describes steady state diffusion, which means the diffusion rate stays constant with time. The law shows that the diffusion flux is proportional to the concentration gradient. In simple words, when there is a large difference in concentration between two regions, atoms move faster. Another important term is the diffusion coefficient D. The value represents how quickly atoms can diffuse through a material. A higher diffusion coefficient means a faster diffusion. One practical application mentioned in the slides is the hydrogen purification using palladium metal. Hydrogen atoms are able to diffuse through the palladium sheet, while other gases cannot. Because of this property, palladium can be used to separate and purify hydrogen gas in industrial applications. After that, we looked at an engineering example involving methylene chloride diffusing through a butyl rubber gloves. This example is important because some chemicals can pass through a protective materials and become dangerous to humans. In this problem, the goal was to calculate the diffusion flux through the glove material. To solve it, we used Fick's first law together with the given values: the diffusion coefficient, the glove's thickness, and the concentration on both sides of the glove. The example showed how diffusion equations can help engineers determine whether a material is safe for protection against chemicals. Next, the chapter introduced non-steady state diffusion. Unlike steady state diffusion, here the concentration changes with time. This means the diffusion rate is not constant anymore. Because of this time dependence, Fick's second law is used instead of the first law. The graphs in the slides show how concentration changes inside material over time. For example, atoms diffusing into aluminium gradually move deeper into the material as time increases. At the beginning, the concentration is highest near the surface. Then, as diffusion continues, the atoms spread further inside the solid material. One important graph in the section shows concentration versus distance inside the material. The graph explains that near the surface the concentration is high, and as we move deeper into the material, the concentration decreases gradually. It also shows that after more time, diffusion reaches deeper regions inside the material. We also learned about the boundary conditions and initial conditions used in solving diffusion problems. These conditions help describe the concentration at the surface and inside the material before diffusion begins. Another important concept introduced was the error function equation. This equation is used to calculate the concentration at a specific position and time during non-steady state diffusion. Using this equation, engineers can predict how deep atoms diffuse into a material after a heat treatment or other industrial processes. This is very important in applications such as carburizing steel, semiconductor manufacturing, and a surface hardening. Overall, this section explains how diffusion works, how it mathematically analyzed, and why it is important in materials engineering and industrial applications.